Yeah, so I'll wait for like 2 more minutes, maybe. All right. Hey everyone. So what I have planned for today is to basically look at some midterm questions from previous years that are towards the start of the midterm. And just, like what you're supposed to do is just go through them and do them yourself. So what I'm going to do is just model how I think I would approach studying for that kind of thing. So again, this is specifically meant as kind of the catch-up session. So I'm going to be focusing on kind of the easier ones, which is what you should start with. Of course, like ideally, everyone would practice with everything. So if you have any requests about things that you want to hear about as well, I'm happy to stick around after I do a couple of examples and answer whatever questions you have, stuff like that. So, okay. So, so here's kind of what things basically look like usually. So this is 2023. So this is just, print something, right? So write the function that prints Happy Halloween if the input month is exactly OCT and the input day is exactly 31. Otherwise, the function should print not Halloween. I hope this is kind of straightforward for everyone. With that said, I will do it. And the reason is to just model what you're supposed to do when you're studying. So first of all, and again, for some people, this might be too slow. I don't know, but I'm trying to be thorough here. So one thing that you sometimes see is you read the question and you don't exactly know what the thing is supposed to do, like what did they want from me. So one way to get unstuck is to just say, okay, so I'm being asked to write a function. It has some kind of outputs that I'm supposed to have. I'm having kind of difficulty seeing exactly what they want from me. So just write down examples. So it says, okay, if the input month is OCT, input day is 31, something like this, right? So that means that the example would be if this is OCT and this is 31, this should print Happy Halloween. And then, so hopefully you get that far, and then you say, okay, so if not, so if it's something like this, then it should say not Halloween. One thing to pay attention to here is that it says print, it does not say return. So always print means print, return means return. In this case, it said print. So, okay. So now that we've written down those examples, we can hopefully do this. So this basically says only if that's the input, print happy Halloween, otherwise print not Halloween. So one way to do it is to say if month is October and day is 31, then we print happy Halloween. Otherwise, we print not Halloween. So that's the answer. So I think, everyone who's done the lab, I think, can do it. So we can test it and see that it works. So this prints happy Halloween, this prints not Halloween. So that's great. One thing that's important, especially if you feel like you're struggling, is to actually type in the code and actually try to run it. Because it's very easy to get those things wrong, especially when you're writing on paper. And especially if you don't have feedback, if you haven't practiced, like actually writing the answer and then checking that it's right, and then seeing, okay, like what did I need to fix in order for it to actually run? It might be that you think that you're getting things right, but you're not. So try to type it in, try to actually run it. And the process of actually going back and fixing it until it runs is really important. So the other thing is, as you're studying, so this might not be an amazing example here because it's kind of easy, but this is the example from lab 1. So as you're studying, one thing that might make sense is to say, okay, like, what does this remind me from the lab? If I got it, then I don't really need to know anything more because I got it anyway. But if I didn't get it, if I had to struggle, you could say, okay, like there was an example like that in lab 1 where it was with greetings rather than saying happy Halloween, not Halloween, but the structure was the same. So you say, okay, that means I need to review that question from the lab. So, okay. So let's do another one. So here we're saying write a function that takes in a list of integers and returns the sum of the squares of the even integers in the list. So basically, we want to go through every one of those. And then if it's even, we want to add it to the running sum as its square. If not, then not. So again, I'm going to go here. And I'm going to say, OK, so what is this? This is return 2 squared plus 4 squared. And then I might write another example. So one kind of point of confusion might be, is it like at even positions or is it the even numbers? So here it's the even numbers, not the even positions. So you might say, okay, like 1, 3, what should you return? You should just return 0 because there are no even numbers there. So what are the components of the solution here? So there are 2 components. One is what's called the accumulator pattern. You don't need to know this term. And this is basically set up a running result and keep updating the results until you have the answer. And then the other is what you might call filtering. Go over the list and only use the entries that are relevant. So let me first write this and then go back to kind of how you think about it in general. So I'm going to say, OK, so result initially is 0. Then I'll say for E and L. So that means, for this one, E is going to be 1, and then it's going to be 2, and then it's going to be 4, and then it's going to be 3. And now I only want the relevant ones. So I'll say if E is even, then I'll add the square of E to result. If not, there is nothing I need to do. And then at the end, result is what I want. So I'll just return the result. Okay. So again, if you didn't struggle with it, there's no problem. But if you did, and now you have the solution, so think about it like that. So you have this kind of pattern where you want to come up with the answer eventually. You don't know what it is initially. And the way you come up with the answer is you go through the list or the dictionary element by element and just say, okay, like, what do I do with this element? And this is a very common pattern where you say, okay, like, if there is nothing in the list that's relevant, then the answer is just 0. So I'll just say initially the result is 0. And if none of those things do anything, then I'll just return 0. And then I'm going through the list. So I'm saying for E and L. And I'll say, OK, so if E is even, then this is how I update the result. I add the 2 squared here. And then when E is 4, I add the 4 squared. One very common issue is people try to say something like return result here or something. So that's not the pattern, right? And if you try it, you'll see it doesn't work. And the reason this is not the pattern is you're computing things line by line. So the first time that you say result plus equals is E squared, that's just the square of the first element. Another thing to, again, review as you're looking at this is ways of going through the list. So if you remember, we have 2 ways of going through the list. So you have basically something like this. This is the pattern that we used here, which is E is going to be, in this example, it's going to be like 1, and then 2, and then 4, and then 3. And then the other way that we have of going through the list is like this. It's going to be exactly the same. So L at 0, L at 1, L at 2, L at 3. In this case, we didn't really need to know the location I. So it was easier to do for E and L because this is just extra stuff that's not being used. We're not using the position, right? So when would you need the position? Well, you would need the position if instead of having, in this case, I'm now making up a new question. So let's say that you want the sum of squares of even numbers that are also in even positions. So what I mean by this is now what we'll have is just this, right? Because 4 is in position 2. So that's an even number in an even position. This is an even number, but it's not an even position. This is in an even position, in position 0, but it's not an even number, so it doesn't count, right? So if you wanted to write something like this, then you would have to use this pattern. So for I in range length of L. So that would be something like this. And then we have 2 conditions for when to add into the result. It's if I is even, and also L at I is even. So here we do not have the E. We just can access the element with L at I because we are going through the list using for I in range length L rather than for E and L. And in the same way, we'll return results. Right? So a lot of the time, you'll have situations where you have to go through a list or you have to go through a dictionary. And you just got to say, OK, if I don't need to know the position, then probably this is the easier way to do it because less ways to get confused. If I need to know the position, so in this case, this was explicit, like also in even positions, then this is the only way of doing it. The other example that we had where you need to know the position is if you need to know what's happening with neighboring elements. So if you need to compare L at I and L at I plus 1, because like you want to know like how this compares to this and how does this compare to this and so on, then again, you need to know the positions. You can't get away with just saying for E and L because when you're in here, all that you know is what is the E. You don't know what the neighbors are. Okay. So one more thing that I wanted to say before maybe going to questions is I wanted to, again, suggest coding bats. So this is something that I linked on Piazza as well. So you can do basically everything except for string 2. The warm-up ones are kind of a little bit annoying. The list 1 ones are, I think, kind of a good target if you feel like you're struggling and you need more practice. So, and here, like you could just like plug it in. You can also debug it in Python. So let's just do this example since I clicked on it. So here you're giving an array. So this is not correct terminology, actually. So this is what we call a list of length 3. Return a new list with the elements in reverse order. So this is an example where we technically had kind of the shorthand, right? So we had return nums like so. And that's kind of like the easy way of doing it, right? So like if you remember that this is the way to reverse a list, you can just do it. So if you remember, the reason this is the way to reverse a list is that this is implicitly, let me make it a little bit larger. This is implicitly the same as saying nums starting at length of nums minus 1 and going down to the very beginning in steps of -1. So this means like if you're going through this list, like you start with the last one, and then in steps of -1, you go here, and then you go here. So if you expand it, that's the same as for a list of length 3. It's like nums2, nums1, nums0. And in fact, like they said, it's a list of length 3. So without any fancy syntax, you could also say something like this. Right? So that's the same. Let's take here. So here, like you can just like literally manually say, OK, like you wanted the reverse list that's of length 3. I know what that is. So that's the same. You can also do it with a loop. I think that's actually kind of, in terms of learning, the best way of doing it. That's a little bit more complicated, probably. So I can, again, use this pattern of I start with an empty list. And now what I want to do is I want to build up the list, which is the reverse of the input, the reverse of nums. So how would I do it? Well, I need to append nums at 2, and then I need to append nums at 1, and then I need to append nums at 0, right? So how do I do it? So I need to get to 2, 1, 0. So one way of doing it is to say I want to go from I being 2 down to, but not including -1 in steps of -1. So this would make it so that I is 2 and then 1 and then 0, because you're going in steps of -1 down to but not including -1. So this is this. And now we can say, okay, so you want to append, sorry, result. And we want to append nums at I. And what would happen is first you append this, and then you append this, and then you append this. And at the end, you have the result built up. So that is going to look like this. So this is, again, a quite common pattern where what you're doing is you start with an empty list rather than a 0 or something. And then you're saying, okay, like, what do I need to add to it? What do I need to add to it? What do I need to add to it? Appends so adds the element to the end. So that's kind of the common pattern of building up an answer that is a list. Okay, so I've been talking for a while. So if people have maybe questions or requests or anything else, this is the time to ask. Or like, like if someone feels like, okay, like I need more advice about this or that, that's also a good thing to ask. Right, there's one question. Can we go over Hopfield networks? So I mean, sure. Let me first let me first wait for some different questions than that, because I kind of want to do kind of more basic stuff if there is demand for that. But I can do whatever people ask for.
I have a question about question 5 on the 2023 midterm.
Okay.
I try to do that one, but like in the function description, I think you only have a string as an input.
So question 5.
Yeah.
Okay. Yeah, sorry. So what's the question?
Well, it says that you need to see the occurrence of like some word in the
Yeah,
list,
that's
but then
it.
the def count occurrence only takes like one parameter. Shouldn't it be two, or is there another way to do it? Because I was able to do it like
Yeah,
putting.
you're right. That's a typo. Thank you. Yeah. Yeah, so it should take yeah, so I fixed it probably during the test. Yeah, so it should take the list and then the can.
Okay, thank you very
Yeah,
much.
yeah. All right. Are we doing Hopfield networks? Okay. Okay, so again, like I'm happy to do it. I'm not sure it's going to be like better than just watching the lecture again, but we can do it. So yeah, so just like I mean, like I'm not saying kind of what's definitely going to be or not going to be on the midterm. I didn't actually write the midterm yet, but same as any other example from the lecture and the lab, except for things that we said are not on the midterm. Anything could potentially be on the midterm. And it was on the midterm last year, actually, and it was on the practice midterm. So to that extent, it's like a legitimate thing to ask. Of course, like you also can't have everything on the midterm, right? Okay, I'm just looking it up in the slides. Okay. So, okay, all right. So basically, this is kind of what it looks like, right? So, a Hopfield network is a way of storing what we call memories. So what we mean by memories in this case is just lists of -1 and 1. And the way we store memories is we say we have this network. And this network is basically a picture that represents this formula. So the formula is just anytime there's an arrow, it's like the product. So x0 times x2 times the weight, so times -1. So here we have x0, x2 -1. And then x1 times x2 times 1. So this is this term. And then x0 times x1, this is this term. And then all minus. And then what we're saying is that the actual memories correspond to the minima of the energy function, right? So all it is a way of writing down this formula and then saying, if you've written this formula, then just we're defining the memories as the minima of this formula. So I guess kind of that is all there is to it as the big picture. So do people have questions about this? Like if it's not clear, I'll try to explain as well. But like I don't see faces, I don't see anything, so I have no idea if people are with me or not. Okay. So if there's no objections, I'm just moving on. So okay. So this is kind of what that looks like. So I'm now going to just code this kind of thing from scratch. So basically, my goal now is to make code that computes this energy function and then also computes the minima of this energy function. Okay. So the way I'll do it, and I'll do it kind of vaguely the same way as we did in class, is I'll have the weights, call them S, and I'll store them as this matrix. So the way I'll do it is I'll say Sij is Sij. And then the idea here would be, so okay, so like here we have x0, x1 is connected with 2. So for example, S at 0 at 1 should be 2, right? And then anything that doesn't correspond to an arrow is none. So, okay. So there is no 0, 0, there is no 0, 1, and there is 1, 1, sorry, and there is no 2, 2. So this is like this. So now we fill in the stuff from here. So this is 2. And then 0, 2 is -1. And then 1, 0, there is no arrow from 1, 0. So this is none. And then 1, 2, there is an arrow from 1, 2, and that's 1. And then 2, 2, 0, there's nothing there. And to 1, there is also nothing there. So that's like this. And if you just see, okay, like how many arrows do we have? 3, and we have 3 coefficients that correspond to them. So that makes sense. We caught all of them. Okay. So I'll now compute the energy function. And then x could be something like whatever, like -1, 1, -1. So here, what you're going to do is we're just going to say, okay, so same pattern, actually. So we have a final result. And the result is going to be the sum of everything that's here. So one way of doing it is to just say, okay, like anytime we have a coefficient, we need to add something to the result. So I'll just go through S. So I'll say for I in range length S, and I'll say for J in range length S. So S has got to be square. So with this, and I'll say if the entry is not none, then I'll add Sij times xi times xj to the result. And then the energy is minus this. All right. So what I did here is I said, okay, like go through all of those. And then if it's none, there is nothing to do. If it's a 2, then that means that it corresponds to this arrow. This arrow connects 0 and 1. So do Sij, which is not none, times xi xj. So when I is 0, j is 1, you'll add this term. So 2 times x0 times x1. Okay, so that is a way of computing the energy function. So now the other thing that we did in the lab was to say, okay, like we have this energy function and we can compute it for a particular S. But let's say that we want to get all the minima of the energy function. So try all the possible x's and see which x's produce the minima. So I'm going to do like a little bit of a variation on this so that it's not like the same thing that we already did in a catch-up session. So I want like all the minima. So all the minima don't care about don't care about what the x is. Like you want to say which x's make it so that the E is as small as possible. Okay. So So what I'll do is I'll say, okay, so the current minimum is just the energy for -1, -1, -1. So this is -1, -1, -1. So I kind of avoided having to say 3. So it would work if it's even larger as well, because it just said, well, like as many rows as there are in S, like add this many -1s. It's not going to work for the other things, but it doesn't matter. And S. Okay, so I just plugged it in. And then the current minima, let me call this Kerman value. So far what I have is minus 1, minus 1, minus 1. So what I'm saying is, like, when I start out, the minimal value for the energy is just like whatever I get for minus 1, minus 1, minus 1. And then the minima that correspond to that are just minus 1, minus 1, minus 1. I haven't seen anything else. So now what I'm going to do is I'm going to go through all the possible x's and see if those produce smaller energies. So to go through all the possible x's, I do my nested loop. So this is the usual pattern in terms of how you say, I want like all the possible x0s, all the possible x1s, all the possible x2s, right? So that's just how you do it with a nested loop. If you have questions, I'm happy to do it. But also, like, that's just how you do it. Like, if, x0 could be minus 1, 1, and x1 could be minus 1, 1, and x2 could be minus 1, 1, then over here, you'll get, like, all the possible combinations of x0, x1, x2. So once I have that, I'll construct the x. So here, I made my E so that it takes x as a list. So I'll construct the list. I'll compute the current energy. And now I'm going to say, OK, so if the current energy is smaller than this, then that means that we found a new minimum. So if it's smaller than current min val, then OK, so we found a new minimum. So we got to say current min val is now cur E. And then whichever old minima we had don't matter anymore because we have a new one, which is just x, right? Because we found a value of an energy that's lower than anything that we've seen before. So we just get rid of whatever we had before. And we have x here. So I made a mistake before. So it's a list, but this is a list that just contains x. So the other possibility is that we found a current energy that's the same as the current minimal value. So in that case, what we got to do is we got to add dx to current minimum. If cur E is larger than current min value, then there's nothing we can do. There is a small thing here, which is that here we'll compute the energy for minus 1, minus 1, minus 1, but we already added this to current minima. So one thing I could do is I could just start with an empty list. And then the first time that you compute this, you'll compute the energy for minus 1, minus 1, minus 1. It's going to be equal to current min val. So you'll just append minus 1, minus 1, minus 1 to current minimum. And then at the end, we'll just return current minimum. OK, so this was as an answer to a question. This is like not the thing that I would start studying if I was struggling, which is what this session was advertised for. Although hopefully later in the week, you will. So this is kind of about what we had done in class. Questions about this or anything else? Okay, all right. I'll just pick like one more random question to do, I guess, and I'll just do it. And then if there's nothing else, then we'll just end with that. So what's a good one? Okay, let's do this one. So here we have a list that has whatever professions. And the idea here is we need to count how many times engineer appears in the list. Sorry. So that's actually, again, the same pattern where we have the result, which initially is 0. And then we go through the list. And every time we see engineer, we add 1 to the result. So here, we don't really need to know the position. So it's fine to just say for E in costumes, and then say, OK, so if E is engineer, we add 1 to the result. And then eventually, we return the result once we're done going through the list. So that's kind of like this. Let's do part B. So here, what we want is the smallest factor larger than 1 of this. So the idea here is not that you would do it with math. It's that you just try every possibility until you find something, right? So how do you try every possibility? You just say, OK, so we start with 2, and we go up to n plus. We go up to n. So this is up to but not including n. So up to but not including n plus 1. Sorry. So up to n. And here we'll just say, OK, so if this is actually a factor, so if n is divisible by factor, this is how you do is n divisible by factor. We return factor. And that will definitely eventually find it because you're going, is it 2? Is it 3? Is it 4? Is it 5? And so on. And eventually just get up to n, which is definitely a factor. So you'll return something. And then the function actually asks you to print it. So you would do like print smallest factor. You didn't have to write it as a function. You could just write it as a piece of code as well. But to kind of answer the question, you would say, OK, so I want the smallest factor of this number, and I want to print it. It specifically said print, so the job is to say print like this. You didn't have to do it as a function. So 2 things to note here. So we are here returning right away. The reason we're returning right away, so we're not waiting to return over here, is that we're looking for the smallest factor. And here we're trying the smaller first, the larger later, right? So factor is 2, then 3, then 4, and so on. And then immediately, if we find something that divides n, that means we found our answer because we're trying like the smallest answer, next smallest answer, next smallest answer, next smallest answer. So once we found something that works, that's the answer. So we return right away. We don't do anything else. OK. I think I said that there's 2 things to note. I think that's just the one. All right. Questions about this? All right. OK, that was the 2 parts. OK. Are there any other requests? Or like questions, whatever? Yeah. Okay, so all right, so I'm kind of like staring at empty screens. So I think what I'll do is I'll announce kind of an in-person session as well for people who are struggling, so that hopefully you can interact, because right now, unfortunately, I have no idea if I'm helping or not. Hopefully a little bit at least. So hopefully, kind of, if I can see you, then that would be better. And possibly, this is like, well, I also don't know who showed up. So I'll announce more stuff later. All right. Last chance for questions. Anything?
There are actually two questions on the chat.
Oh, there are.
Yeah.
Oh, okay. Thank you. I didn't see that. Uh, okay. Should we know how? Sorry, so I didn't see it. Okay. Should we know how to do problems involving matrices at the level of difficulty in the past midterms, or the lab involving Gaussian elimination? So, okay, like, look, if you look at past midterms, you'll see that there's always a range of difficulty. I think it is fair to say, so kind of, I think what you're implying, and you're correct about that, that the Gaussian elimination lab was like not an easy lab. That's absolutely true. So I think if you look at past midterms, what you'll see is there is usually like a question, or like a question and a half that's at about the level of difficulty of what you've seen for Gaussian elimination. But like, obviously, most of the questions are not like that. So that's one way of answering it. The other way of answering it is that level of difficulty also depends on what you've seen. So it would be legitimate to ask something that's very similar. So I wouldn't ask like an identical thing, but like very similar to what you've seen on the literal Gaussian elimination lab, and say, okay, it would be extremely difficult if it were something that you're seeing for the first time, but actually everyone's seen it. So that makes it like an intermediate question. So hopefully that answers your question. Like, the short answer is, like, you want to know the difficulty level that's expected, just look at the past midterms, make your own judgment about what's difficult, what's not. Where can we access notes for each topic we've been taught? So currently they are all linked from the slides. So unfortunately, yeah, so like, let me acknowledge that like the website could be better organized. I'll get on that as well, but everything is linked from the slides. The memory, can we go over the memory address stuff? Okay, so I think that would be kind of challenging to do in the next 15 minutes, just because it's like a big thing. So I think what I will do is I will like refer you back to the lectures and to the memory model notes. I will, however, do a few examples as a compromise. So like, it's just hard to like go over it, because it's like, like, even if I go fast, it would be like an hour or two. So uh sure. So just one sec. So okay, so let's do those ones. So this one you can actually just do by eye, right? So so here, like, there is something that's printed here, something that's printed here. So sorted doesn't print anything. And we also know from last lecture that there is no way that you can modify the contents of S, right? So that means that this prints ABCD and this prints ABCD, and that's it. So there's nothing that's going on there actually. Okay. And the way you know is there's like you're not saying S is something new. This doesn't print anything. There's no way that it can change the contents of S. Nothing can change the contents of S because S is a string. So S was ABCD, S remains ABCD. Let's do this one. So, okay. So we are over here. So I'll do it kind of with Python tutor, I guess, this time. So here L is a list. And the first element is 1. So it's displayed here as just 1. Of course, it would actually be an address. And then the second element is this list to 3. And then the third element is 4. So if you remember, this is a shallow copy. So what's happening here is on the right-hand side, we have a new thing. So this will go in the memory table. And then we also have a new list L1. So here's what this looks like. So we had L, and now we also have L1. So those are two lists, two different variables. But what happened is the address L1 just got copied to the address L11. So if you go back and look at the notes about shallow copies, this is exactly the kind of thing that happens, right? So you do create a new list. So L and L1 are different lists. However, L at 1 and L1 at 1 are aliases. So you then go and say, okay, L at 0 is equal to 7. So the intuition here is L and L1 are different lists. So L at 0 equals 7 is going to change this. L at 1 at 0 equals 8. So L at 1 is this. L1 at 1 is also this. So L at 1 at 0 is going to change this guy. So that means that whether you access it via L at 1 or via L1 at 1, it's going to matter. Right? So now L at 1 at 0 is 8, and also at L1 at 1 at 0 is 8. Now we're going L1 at 1 at 1. So it's the same. So L1 at 1 is this guy. So this is now going to be 9. So basically, what's happened is this 2, 3 got modified to 8, 9, right? And then L and L1 differ in that their first elements are different because we said L at 0 at 7, but L1 didn't care. So that is the result. So it's not like an ideal thing to do over Zoom, just because like I don't really have kind of people's reactions, and it usually takes like this is the same as the exercise C from the worksheet, so it like takes a while to digest. But this is basically the gist of it. Does this make sense? Question.
How come the list 2, 3 is shared amongst both L and L1?
So yeah, so like that's the main thing that's going on, right? So that's what happens with shallow copies. So when you have a list that's like this, and then you say L1 is a shallow copy of L. So that's the same as saying L1 is L at 0, L at 1. So what happens is L1 is a new list, but you're not creating a copy of 1, 2. You're not creating a copy of 3, 4. You're just saying, okay, whatever the address was for this one, we'll write the address here. Whatever the address was for this one, we'll just write it here.
Okay, thank you, sir.
So, okay, so there's another question in the chat. So what if you did L1 equals L? So I guess you mean over here, right? So if you say L1 equals L, then L1 and L are full aliases, which means that whether you say L or L1, starting from there on until you say L is something new, L1 is something new, L and L1 are just going to have identical contents because they're the same list. Make sense? So if you say, so I think that was the question. So now the picture here is going to be L is this one and L1 is this one. So whatever you do to L happens to L1 and vice versa. So the question here is, what if you did it in an integer? They won't be full aliases. The answer is yes, actually they will be. So the issue is that integers being aliases just doesn't matter because you cannot go and change the contents of an integer. So technically, they absolutely would be full aliases. It's just that you don't need to think about it. Right? Okay, all right. So there was a request for dictionaries. So if A is equal to 1, B is equal to A, so no. So that's different, right? So and this would be the same with dictionary with lists, right? So if you're saying A is equal to something new, then A is equal to something new, right? So this is not the same as changing the contents, right? So here, when we're saying L at 0 equals 7, then we're changing the element 0 of L. And that means that element 0 of L1 also changes. If we had said L is something new completely, so if we said L is equal to 7 rather than L at 0 is equal to 7, then now L and L1 are separate again. So if A is 1, 2, 3, B is equal to A, so now B and A are aliases. At 1 is 3, correct. Yeah. So yeah. Okay, all right. So the request was for dictionaries. Can we define objects in Python? Yeah, you can, yes. So like in principle, like technically, like anytime that you make a list, that's kind of like defining an object. But I think you're asking about like defining custom objects, and the answer is yes, you can. Yeah, but we haven't done it yet. Okay. All right. So like dictionaries, like what we did was mostly like problem solving, and dictionaries is like actually nothing much, right? So basically what a dictionary is a bunch of key value pairs. So you have keys, so those have to be immutable. So in practice, keys cannot be dictionaries and lists themselves. And then you have corresponding values. You can access the corresponding value using a key like this, in the same way that you would access an element of the array using, grades at 0, grades at 1, and so on. You can modify those. So unlike with lists, you can actually say, okay, like there is like a new entry with a new key with the corresponding value. You can do it. So this is linked from slide 20 from week 8. so the slides are linked from the main slide deck. Sorry about that. So if you go to the main slide deck, there is a link to week 8. Okay. So, all right. So that's great. So you can do it with, keys being integers. So unlike with lists, those integers can be arbitrary. So what else can you do? You can have something like this as well. So values can be dictionaries themselves, whatever. Like we mentioned on Friday, keys have to be immutable. So you cannot have like grades L. So you can go through you can go through a dictionary by using something like this. So this is the default way that we do it. We say for subject grade. So this is like for key value in the dictionary name dot items. And what you get is the value and the key. So if this is the items, then or like the key value pairs, then this would be like Civ 100, and then Math 95, and then CSC 87, and then ESC 95. So that's basically all there is to it. Kind of everything else is kind of just examples. Right? Right? Other questions? All right. Okay. So if there's nothing else, I will see you next time. Okay. All right. See ya. Bye.